Hello and welcome to this AQA Further Math Statistics video, the third in the series looking at chi-squared tests and contingency tables. And this video is building on the work done in the second video in the series, so you want to remind yourself of what we did then. And this video is actually looking at carrying out the test following the work we did in the previous video. So as usual, we need to state our hypotheses, and the hypotheses are that there is no association between hair and eye colour using the contingency table that we started off with. And our alternative is that there is some association between hair colour and eye colour. And we're going to be using those tables of observed and expected values that we found in the previous video to do this. So as usual, our null hypothesis is just that there's nothing out of the ordinary. We'll test at the 5% level of significance. We'll assume that our null hypothesis is true, and that's what we did in the previous video when we found our expected values, assuming no association between hair and eye colour. And then we will find a measure, we'll find our test statistic to see whether those observed values could occur purely by chance, or whether that actually is not the case and we need to reject our null hypothesis. And to do this, we're going to use a new distribution to you, the chi-squared distribution. This is a continuous distribution used for tests of association on contingency tables, and it just has one parameter, nu, and that's the number of degrees of freedom of the distribution involved. And you'll see where that comes from later on in this presentation. So if you recall from video 2, we had our observed frequencies of 131 people and their hair and eye colour, and we also worked out the frequencies we would expect to have if hair and eye colour were completely independent. And our test statistic here is given to you in the formula book, and it's a way of measuring the difference between observed and expected and looking at how significant those differences are compared to the size of those differences and the value we actually expect. So obviously a large difference on a small expected value is more significant than a large difference on a large expected value. And if we just look at how this is evaluated, we would do 7 minus 8.85 squared divided by 8.85. And if you work that out, you should get 0.387. So keep a few decimal places in here. And that needs to be done for all 15 of these O and E pairs of values we've got here. And notice that O minus E, the difference there is squared, and that's because some will be positive and some will be negative, and we need some way of getting over that problem of negative and positive values cancelling themselves out. And this is very much like we do with variances. And just so you can check in this table here, each O minus E squared over E is written down here for each of the categories we've got. So our test statistic, if you recall, is the sum of all of those. So that would be our 0.387 plus 4.149 plus all those 15 differences, 0.079. And if we total that, 19.717, and that's our test statistic, and that's going to tell us something about the size overall of the difference between our observeds and what we'd expect if eye and hair colour were independent of each other. And you can obtain this test statistic directly from the calculator. It might be slightly different because it uses greater accuracy, but do remember that actually these individual contributions are very important when it comes to your conclusion. So if we now look at this nu with chi-squared, every contingency table will have, that we're carrying a chi-squared test on, will have a degrees of freedom associated with it, and that's simply the number of variables that have freedom to vary. So what does that actually mean? Well, because we must retain our row and column and overall totals seen here in red, it actually means that when we work out our expected values, we only, for example, here with black hair, we only need to work out those two, and then this one can be obtained by subtracting those two from 29. It's fixed. And similarly across here, if we work out for blue eyes those four, the other again is fixed because our row there must sum to 40. So looking again at degrees of freedom, actually we just have these 8 values that are, if you like, our free variables. The others have to follow because of the totals. And for this contingency table, the number of degrees of freedom is actually 2 multiplied by 4, which is 8. And the rule for our degrees of freedom for a contingency table is always that it's the product of the number of rows minus 1 multiplied by the number of columns minus 1, because of the need to have the totals matching for observed and expected values. So for our critical value, and remember we have a 5% significance level, we're going to go to table 2 in the formula book. We're going to find our 8 degrees of freedom here, and chi-squared tests are always one-tailed tests, so we want the top 5% here, and that means that P is going to be 0.95. And they're always one-tailed tests because we're trying to see whether the differences between what we've actually observed and what we'd expect if eye and hair colour are independent, are they close enough or are they so different that that's going to lead us to reject the null hypothesis. And our critical value in this particular case is 15.507. So to complete the test, we have a critical value, perhaps I'll put that here, of 15.51, and our test statistic is 19.72, clearly in this top unlikely 5% area, and therefore we're going to reject the null hypothesis, and you would get the same conclusion if you got a slightly different value using the calculator. And also if you use the calculator, you might just like to quote the p-value and compare that to 0.05, the significance level. When it comes to making your conclusion, we're rejecting H0, but we need to make the conclusion now in context. And then if we do reject the null hypothesis, we need to find our strongest sources of association and write down what those ones are. So here we definitely are rejecting, so our conclusion in context, and it mustn't be definite, we don't definitely know there's an association, so we say there's sufficient evidence at the 5% level of significance to suggest that there is an association between eye and hair colour. So our conclusion led us to reject H0 and conclude there's evidence that there is an association between hair and eye colour, and in order to determine what that might be, that association, we look at the contributions to the test stat and we identify the largest contributions we can see. Possibly these three are the largest, most significant contributions we have. And then if we compare the observed and expected, we can then comment on what's going on. So we would expect just over 6 blonde with blue eyes, and we've got 10. So it appears more blonde people have blue eyes than we would expect. There's an association there. We also have far more black-haired people with other coloured eyes than we would expect, so an association there. And if we look at brown hair, we have far more people with brown hair and brown eyes than we would expect. So again, we have an association there that we can talk about. So here is a summary. You might like to just make a note of all of that, what to go through when creating a contingency table, and carrying out a hypothesis test for association. And that concludes this video.